Okay, now I think it's time to start. So I welcome everyone on our sixth lecture of our astrochemical lecture course. This lecture will be given by Professor Edwin Bergin from University of Michigan. He will speak about astrochemical observations and theory. So please, Edwin, the floor is yours.
Sure, thanks, Sergey. So greetings, everyone. What I'm going to be talking to you about today is not the sort of gee whiz, this is really cool observations of astrochemistry. I'll show you some of that for sure. But what I wanted to convey in this lecture is the how you do it. That is how you take an observation and extract salient quantities. That is what we have to do as astronomers. And that requires an understanding of how molecules get excited, how they release that radiation, the radiation transfer, and the same thing goes for the solids. So we actually have to physically understand what is going on to extract the information and understand how stars and planets are born. So there's going to be lots of equations and things like that, but this is the important stuff that one has to use to essentially be an astrochemist. And I'll start here with this picture. This is carbon monoxide in the galaxy. This is 2001 when this first came out. The first map of the galaxy was in the 80s. That inspired me to do what I'm doing today. And that's just a view of this. There's information in that image. That is emission from carbon monoxide, where you see it's red is stronger emission and green is weaker emission. And that's telling you something about the galaxy. This is let me go back. This is the Taurus molecular cloud, seen in an optical photograph taken by E. Barnard in the 1900s. You see those dark patches against the star field, and they see the size scale on the left there. That's about 20 parsecs in skies. And again, a parsec is about 3 by 10 to the 18th centimeters. So this is a lot of space here. And if I were to look at this with carbon monoxide eyes, that's what it would look like. So the dark areas on the sky are filled with material. That's where the molecules are, and indeed that is where the stars are being born. And so now I'm going to zoom in to this area here, where you see this filament. And if we observe that with a different tracer, this is dianzanilium, N2H+, this particular molecule, as I will show you, traces denser gas than carbon monoxide does, and we know why. And what you can observe is that filament breaks down into a series of smaller condensations, and those condensations are where stars are actively being born. And I give you densities. The densities of those little knots are of order 10 to the 5th particles per cubic centimeter. The typical density, average density of the galaxy is 1 particle per cubic centimeter. So these are overdense regions, which makes sense, right? Material has been collected on its way to making stars. And the temperatures are very cold, only 5 to 10 degrees above absolute zero. And one might ask the question, how do I know those quantities? And that's what we're going to work through today. So this is the process of star and planet formation. I start out here. I have a cloud of material, and the cloud has some sort of filamentary structure that's related to how the formation mechanism of the cloud itself. And inside the filaments, regions become overdense and begin to collapse under the weight of their own gravity, or perhaps are pushed. Things are rotating. So those cores that I showed you there are rotating. All right. And the rotational collapse, to conserve angular momentum, it leads to the formation of a star in the center and a disk of material. and the disk is accreting material from the natal envelope onto the star. Again, conserving angular momentum, you get these protostellar outflows. And there's a energetic outflow, and there's also winds filling this cavity, and that's what's basically ablates the envelope over time, and you're left with a dense disky region, and that is the region where planets are born. And the techniques that I'm going to describe to you today are applicable across this landscape, even into comets and planets. So to give you an idea of what happens in the galaxy, let's start first with the gas. So this is the characteristic gas density here, and this is the approximate size of solids. So I'll start with the gas. Much of the mass of the galaxy is in what we call the warm neutral medium, where it's very hot, thousands of degrees Kelvin. Everything is relative, okay? So when I say very hot, I mean, thousands, 500 degree Kelvin. But if I were an X-ray astronomer, hot is millions of Kelvin. All right, so it's always important as astronomers to qualify what you say is something is hot or cold. That material has an average density, a characteristic density of order unity. There is a shock that passes by that shocks the material, heats it up, and when it cools, the material gets denser. All right, as it gets denser, the material gets collected together. You have the gas and also the solids. The solids get dense enough to extinct starlight, which is destroying molecules. So basically, UV light from the galaxy keeps the most of the material atomic. But when you get dense enough, you can start to shield material, and that's where CO forms. And as things get denser here, that's during the core condensation phase, other molecules form, ices start to form, and you get to order 10 to the fourth, 10 to the fifth, and then collapse occurs. And you get to what we call the protostellar phase, the disk phase. The densities can get even higher, obviously, in the part where you make the star. And eventually the gas goes away or gets dissipated by the winds from the star and maybe the radiation. So there's an overall evolution, an evolution towards higher density. The dust is doing roughly something similar. And here, instead of density, I'm tracking size. The average density or average size of a dust grain, the solid, the galaxy is filled with gas, mostly hydrogen, and tiny little solids that are of typical size of 1/10 of a micron, and they're mostly silicates or carbonaceous in content. So we know these silicates. We're sitting on a gigantic rock that is made out of these interstellar silicates. So minerals are things like glass and sand, right? Okay, well, the dust stays basically constant here, all right, in size, and nothing happens to it until you get to the densest parts of the evolution, and then the solids start to grow, okay? And when I have the collapse, they grow, and it's in the disk that some magic happens that we call the streaming instability, where these solids get to about a centimeter in size or so. And then an instability occurs that collects them together, and you have an over-dense region of solids, and you make basically what I call cometesimals, but we typically call them planetesimals. A cometesimal would be an icy body, and this was a review for comets 3, so you can understand how it might be a cometesimal. And so you can see how, the cosmic size of solids is over an insane range of size, right? So you're going from 1/10 of a micron, so you get to say the Earth of 6,000 kilometers in diameter, right? Or in radius, I'm sorry. So, okay, solids go through growth, the gas gets denser, and we want to understand how we know this. And this is just another saying that this what I've been talking about here is not something we don't know. We have gorgeous and wonderful and beautiful observations that demonstrate what I'm talking about. So you see here the Orion molecular cloud. If you look in the constellation Orion, and just below the belt, there's where the sword is. That's where the Orion molecular cloud is found. And that's what it looks like in the dust emission. It's not even dust emission. The dust scatters starlight. So I'm looking at the structure of the dust condensations that are scattering starlight. And here's a molecule that's showing you the dense gas where stars are being born. When some stars are born, some of them are massive, many times more massive than the sun. They ablate the surrounding material and irradiate it. And this is what's called a photodissociation region. So you can see this is the horse head where we have this ionization in front. No molecules here, molecules downstream below where the radiation is being absorbed. And that's what it looks like in a different molecule. This is a dense prestellar cloud. And this object is denser here, lower density here. It's on its way to making a star. And here's a star with a disk. We don't resolve the disk here and the molecular outflow. Binary protostar here. And this is a planet-forming disk seen in the dust and a planet-forming disk seen in the gas. And what we're looking at here, this is dust emission, the emission of millimeter grains. And this, I think, is, let's see, formaldehyde. So how do we extract information from observations such as what we're looking at here? Okay, so stars and planets are born out of regions dominated by molecules, but also by solids. We're astrochemists, we're after composition. So I need to have an abundance relative to some standard. And of course, that standard is hydrogen, right? That's the most abundant element. To do this, I have to understand how the molecules emit. And as I tell my student, each molecule is its own story. It's quite a pain. So we have to understand the molecular physics and the molecular astrophysics. How do I determine the quantities, density, temperature, and this other quantity called column density? And column density is, put simply, we don't resolve along the line of sight. Everything's on the plane of the sky, right? So I can measure a volume density via very creative techniques. And I can also measure the column density, molecules per centimeter squared, along this line of sight within the resolution element of my telescope. All right, so that's another quantity. And we need to have our standard. How do we measure the standard? And I'll present how we do this, and I'll give example. I'm not capturing everything, but I am going into the details. And I won't be talking about telescopes in this. Okay, so astrochemists, we have to know molecular physics. This is the Bible right here, Townsend Shallow. Why is that the Bible? It's still published and it's cheap. The Herzberg has multiple volumes. It was insane what that gentleman did. They're hard to find and expensive. Gordy & Cook is out of print. And this you might be able to find online. It was a nice little thing that I found that helps me learn a little bit. Okay, so a molecule will only interact with radiation if it has an electric or magnetic dipole moment or potentially a quadrupole. And usually what this means is that you have some asymmetry in the distribution of charges. That is, the electrons are distributed differently. So if I take the water molecule where the hydrogens stick out, like Mickey Mouse ears, all right, it turns out that just because of the way the hydrogens are structured, the electrons like to hang out near the oxygen atom, and the positive charge therefore is more distributed towards the hydrogen atoms. So when the water molecule spins, it's like a little antenna. All right, and it's radiating or receiving radiation at particular frequencies. All right, so that's a dipole moment in this example. Now, atoms, if you solve the Schrodinger equation for the hydrogen atom, right, you determine the electronic states. All right. Molecules have electronic states as well. All right. But they also have the nucleus that might have some structure. And you take the water molecule, right, where the two hydrogens are going off. It can rotate, it can vibrate. Okay, so the nuclear motions and the electronic motions have to be considered here. And that picture there is just showing I thought that was so cool where they actually took a picture of the electron cloud in this one particular molecule. And so the total energy of the molecules consists of the kinetic and potential energy of both the electrons and the nuclei. All right. Now, so similar atoms, we expect different states depending upon electron orbitals, but the electrons are lighter than the nucleus by quite a bit, right? They're zipping around for many cycles of the electronic motion. The nuclear is doing less, right? So the assumption, and this assumption is called the Born-Oppenheimer approximation. And indeed, you can watch a movie about the Oppenheimer in this attribution. He is known as the father of the atomic bomb. But what he first started in the study of quantum mechanics, he looked at molecules, and Born actually said it should be the Oppenheimer-Born approximation. And what that is that you treat the electronic motion considering the nuclei as fixed. And the electronic energy of the state depends upon the internuclear distance. That makes sense, right? Because the positive charges, if they're tightly packed together, that has a different potential than if the positive charges are separated. Okay, so I haven't done this, but other people who are very smart have solved or attempted to solve the Schrodinger equation for molecules, which is very difficult to do. But we can come up with some very simple approximations. And this is actually kind of cool. All particles are confined to a volume with a diameter that is a typical diameter of a molecule, and that's generally 1 angstrom. All right. And each particle in that thing has an average momentum of h, the Planck's constant, over 2 pi r. Okay. And we have the uncertainty principle. There's the momentum here, and the distance is equal to h over 2 pi. So the kinetic energy in the system will have spacings of basically the change in the momentum squared over 2 times the mass. All right, and this just breaks that down as to what the momentum is. All right, it's h squared over 8 pi squared times the mass over radius squared. So if I keep the radius fixed, 1 angstrom, what changes is the mass of the electron versus the mass of the protons. And if you look at that, the kinetic energy of the electrons is of order 10 to the 4th Kelvin, all right? So the electron motions. And the nuclear motions, if you work it out, which is the rotation, are actually in the milli EV range as opposed to the EV range. So of order 10s to 100 Kelvin. So these two things are different. They're tracing different conditions in interstellar space. What does that mean? Quite simply, if 10K gas will not have much electronic motion or emission, and 1000K, 10,000K gas can have electronic emission. Okay, so what we have is electronic transitions, typical energies of about a few EV. That's in the ultraviolet parts of the spectrum. There's molecules can vibrate a bunch of different ways. It's insanely fascinating. And the typical energies of those motions are of order of 1/10 of an EV, and that's mostly in the near to mid-infrared, a very big thing today with the James Webb Space Telescope. And the rotational transitions are found in the sub-millimeter, millimeter, centimeter And for the lighter hydrides, such as water, the lighter molecules can even emit in the mid-infrared. So the James Webb, we see a lot of water rotational emissions. And there are the typical energies of the rotational emissions. So this is what it looks like. You have a potential energy of this is what say a diatomic molecule here. This is H2. All right, so this is basically the separation of the hydrogens. So there's a potential, and within that potential, I have a bunch of vibrational states. All right, these are different electronic states. And why do this molecule have these different electronic states? You look it up. And like I said, each molecule is its own story. They have different states and they do crazy things. This is a dissociative state. So a molecule in the ground electronic state could absorb a photon to put it in an excited electronic state. And then you would get a series of emissions of vibration and rotation cascades going through the various electronic states and vibrational states and rotational states until you get back towns at the bottom. And this is just showing you that for each vibrational state, you have different rotational states. It's like I said, each molecule is its own complicated story. So to break this down, this is temperature and density. All right, if I look at interstellar space, I have the diffuse gas, which is of order 1,000. It's a little bit warmer. That's stuff that's probably on its way to making dense condensations. Regions that condense get colder and denser. Why do they get colder? Because the effects of starlight get removed as the grains absorb the radiation from stars and efficiently radiate it away as more and more grains get concentrated into a smaller space. Stars are born, things get denser and hotter. And then I go on to a planet-forming disk where you get a whole range of densities, temperatures, depending upon where you are with respect to the star. And if I look at that, this is where I would apply lower rotational states of a variety of molecules. This is a regime where I could look at all kinds of organics, which also can have vibrations, and I'm not going to get into torsional motions. Vibration and rotation lines, cascades are up here. Okay, so this is all, excited rotational states, or light hydrides can have their emissions at those temperatures. And electronic transitions would be way up here. So you can see how you could apply different sets of transitions to look at different energy states, and you might be able to then construct what's going on in star formation, right? All right, so now we have to get into the nitty gritty. I have my rigid rotors here. This is what, for simple diatomic molecules, you can think of them as just sort of like two balls stuck together, like what that CO is there that I just showed you. Okay, and that's called, you can assume the bond is rigid, and you can actually work out where the rotational state would be. And the way this works is you have an angular momentum here, that's that quantity. This is the moment of inertia, all right, and that's the angular frequency. Has a certain energy, and I can work out that energy in terms of the angular momentum. The angular momentum is quantized, all right? And so there's a quantum number, and of course that's the famous h constant divided by 2 pi, all right? The energy levels of this motion can be worked out. It's 1/2 h bar squared over the moment of inertia times my different rotational states, all right? And what I do is I gather everything together into what's called a rotation constant. The angular momentum here, the moment of inertia depends upon essentially the mass of the nuclei. All right, so what that means is each molecule with a different mass would have a different, what we call rotational constant, and correspondingly, it will have different energy spacings for its rotational motions. And since this is a dipole, it's the rotational emissions as well. So that's what that happens here. So the electric dipole, the change in that quantum number is plus or minus one. And here we are. Here's the change from J equals one, the J equals one state to J equals zero. That's got an energy that I can determine by that quantity that I showed you earlier of about 5.5 Kelvin. And energy, right, is equal to the Planck constant times frequency. So I know the Planck constant, the frequency of that emission is at 115.271 gigahertz. So if I take my radio telescope and I tune it to that frequency, I can observe carbon monoxide. And I can observe higher rotational states, such as the J equals 3 to 2. And why is it J equals plus or minus 1? Something to do with the molecular physics of that molecule and the selection rules that are allowed based upon the rules of quantum mechanics. So this is pretty neat. When radio astronomy first got going, CO was the first molecule detected by Bob Wilson of Penzias and Wilson fame, the CMB. Other molecules soon began to be detected, and they would detect a rotational line at a certain frequency, and they would then look at different moment inertias of different molecules and ask, well, which molecule could this be? And many molecules were first isolated via that simple equation that I showed you earlier. And again, I'm going through this in a short period of time. This is like information overload, I get it. But it's all here in the slides, and you could always go back to it at any time in your career, right? Now, different molecules, that's the rigid rotor. You can have molecules that have some symmetry, such as ammonia. Ammonia has the 3 hydrogens going off at particular angles. This is what's called a symmetric top. What that means is there's three ways something could rotate nominally, right? It's in one plane and the other plane, and then towards you. Okay. An ammonia molecule, or let's look at it this way. I could have a molecule like here. This is hydrogens coming off like that. All right. So this thing could rotate this way. It can rotate towards us, right? Or these 3 hydrogens coming out here could be spinning. All right. So 2 of these modes are degenerate. This one and this one, they're basically the same thing. But when the hydrogens are spinning, that's a different motion. So there's 2 different moments of inertia. And an asymmetric top is something where there's no symmetry. So water is a metric top. And these get even more complicated. All right. So now I'm an astrochemist. Okay. I want to know how I can determine an abundance from an observation. So I showed you a picture of N2H plus in an object, and that was work that I did. All right, so N2H plus in an object where the N2H plus was centrally concentrated. All right, and I needed to extract the abundance of that molecule. How the heck do I do that? What I'm looking at is in a rotational emission. All right, and to do that, we have to understand excitation. So sorry to go through this, but this is astronomy 101. We got to understand these quantities and how to operate. So what we do is each molecule state, given, say, CO, at a given density and temperature, will have a certain number of rotational states that are populated. We'll call one of them the upper state and the other one a lower state. So the J equals 1 state and the J equals 0 state. The J equals 0 being the ground state. And J here is, again, that quantum number. Okay, so I have an upper lower state that's in particles per centimeter cube. I can also define something called the fractional population, where I have the total density of the molecule and the number density of molecules that exist in a given state. So maybe 10% of the CO molecules are in the J=1 state. Okay. What is the total density of a molecule? Well, that's the abundance of that molecule normalized to hydrogen times the space density of H2. Okay. And capital small n is density, capital N is column density, molecules per centimeter squared. Okay. What we observe is an intensity. Okay. That is the molecules, there's a certain amount of molecules that are emitting, and they're emitting from a certain area in the sky or spreading out, okay, into an ever larger and larger volume. There's a certain energy associated with that emission. So energy per second, how many molecules are there, how far is it diffusing out into space, and it's at a certain frequency. Because these, right, I'm tuning my telescope to where CO is in frequency space. All right. We also have something that we call the flux density, where it's this specific intensity times the source size. So that's in steradians. Okay. So now for the fun stuff. Molecules, everything in space can get emitting in a whole bunch of different ways. All right. So when I talk about the J=1 state versus the J=0 state, well, if you're at 3 degrees Kelvin and 1 particle per centimeter cubed, in general, your molecules, if it were existing in that medium, everything would be in the J=0 state. But as you get denser and denser, or as a star is in the vicinity, you could get things to excited states. Okay, so you get something that takes a molecule that's sitting here in the ground state and excites it until it's in an upper state, and then it can spontaneously emit a photon, and that's the photon that I observe. Okay, so there's different ways that can happen. That is, a molecule might absorb, a CO molecule might absorb a photon at 115 gigahertz. It has to be at that exact frequency. That can put it up into the upper state. Okay, when it's in the upper state, it can spontaneously go down, and that's why I can observe it. All right, and another possibility is you could have a molecule that's in the upper state that observes a photon at the same frequency, 115 gigahertz, and that can lead to what's called stimulated emission, where you can get multiple photons emitted. All right. Again, I don't expect anybody to process all these crazy equations, but they will forever be at your fingertips. What I want to focus on here, this is thermodynamic equilibrium. That is, much of molecular clouds are in close to, or what we call local thermodynamic equilibrium. That is, the particles have a Maxwellian distribution in velocities at a given temperature. The populations, the atom and molecular populations, follow what's called the Boltzmann law. That is, where the space densities in a given state, this is what are called the statistical weights. You can look that up, is equal, and this is the change of energy, that's h nu, and that's a given temperature. So at a given temperature, the molecules will have populations that generally follow this equation. I'm not going to worry about ionization. And the radiation is given by the black body function, that molecules actually emit as black body emitters. All right. I'm going to skip down a little bit here because I don't want to get too technical. That is, this will all be at your fingertips and you can look at it yourself. The key points here is when we observe a molecule, all right, what matters is the molecular emission what I call optically thick or optically thin? So what is optically thick? Optically thick is looking at your wall. I can't see through to the other side. What is optically thin? It's looking out at the glass and seeing through it. Okay. And basically everything that is emitting in space may be optically thick or optically thin. And if a molecule is optically thick, then I'm only seeing the surface of that object. All right. And if the molecule is optically thin, then I'm seeing all the way through the object itself. And as an astrochemist, all right, if I want to measure how much of something is there, I need the emission to be optically thin. All right. And this is the equation of radiation transfer. You have a molecule that's at a black body at a certain temperature. Okay. That temperature may or may not be the gas temperature. We'll talk about that. It has to be emitting at a temperature that's higher than the cosmic background or the local background. And then it's 1 minus e to the minus tau. So tau here is the optical depth. If tau gets much, much greater than 1, this goes away. All right. And tau is what is giving me the amount of a molecule that is there. All right. That is, I no longer have the ability to determine how much of something is present. All right. And the key point that I then want to get to in the next slide is I can take an observation, all right, of my intensity. And from that, I can derive the column density of the molecule in a given excitation state, all right, that is giving me that emission. Now let's think about that. I have CO, here we go, the 0, 1, and 2. And these are my different rotational states. Let's suppose I'm observing this one right here. Okay. What this is telling me is when I observe this photon, that photons that are coming to my telescope, I can determine the column density in this case of molecules that are in that upper state. All right. So that's something, but what if, the conditions are such that most of this molecule is sitting down here in this state. All right. Then I've not measured the total emission of that molecule. And if I want to get an abundance, I need to correct for everything that I didn't observe. In other words, I'm only observing this state here. There's all these other states, and there's states even higher up. And I have to correct for that. All right. So that's the other thing we have to do is I'm only observing one little snippet of that molecule. I can ask, well, what am I missing? Okay. Well, to do that, that's where we get into the fractional population. Okay. That is the fractional population, if I'm in local thermodynamic equilibrium, is equal to a statistical weight, and the statistical weight for a rotational line is 2j upper plus 1. Okay. And an exponential at the energy of that state, say the j equals 2 state, like I did, and some measure of the temperature. So if I have to assume a temperature, and I'm going to talk about how we get temperatures next, and then that is normalized to the partition function. And the partition function, you just have to take a stat mech class and you'll get bored of the partition function very, very fast, is just that quantity there. So what do I mean by that? That is, if I observe the j equals 2 state, and I'm in a condition where I think this equation applies, which is generally what we do, we assume it applies, then I can estimate that only 10% of the population is in the j equals 2 state. I divide by 0.1, and voila, I have my total column density of CO. And if I know something about H2, boom, off I go, and I can get abundances. All right. Well, I'm going through this stuff, and there's so many layers here. Another layer is, well, how do I know emission is optically thin? And well, the beauty of molecules is I can observe different isotopologues of the same molecule. They have lower abundances. The optical depth depends upon very acutely on the abundance. The more abundant isotopologues are more likely to have optically thick emission than the lesser abundant isotopologues, such as that one. And I know these elemental isotopolog ratios, isotopic ratios, from lots of different studies and the references that I give you there. So, for example, I can actually derive the optical depth from my observations. I have an observation of 13CO and C18O, in both in the say equals J equals 1 to 0 state. It equals these quantities. Again, I'm not going to get into the specifics here, but from this, I have an observation of an intensity. This is all the same thing. There's the black body at a certain excitation temperature. I'm ignoring the background here. 1 minus e to the minus tau of 13CO, black body of C18O. 1 minus e to the minus tau of C18O. All right. It's the same molecule. They should have the same temperature. And I know the optical depth of 13CO is greater than that of C18O, because optical depth depends upon abundance. Okay. And I also know the isotope ratio of 12C to 13C and 16O to 18O. So that's 1/7. So what that means is the C18O optical depth is 7 times lower than that of 13CO. So I can work this out. I just take the ratio of the observed emission. This stuff goes away. That's the same quantity. The 13CO is likely to be optically thick because it's the more abundant isotopolog. So that's just 1. And so I get 1 over this quantity. What that means is this observed quantity can tell me what the 13CO optical depth is. I can derive it directly from my observations. So off I go. All right, I'm going to skip that one. All right, now, what I've described to you in very detailed is how I get, say, a CO column density. All right, so I observe one rotational state. I assume a temperature. I apply my magic formula, and I can get the column density of CO in that upper state, and then determine the total column density by determining the fractional population. That doesn't get me to abundance. I need to know what is going on with hydrogen. And this is another one of the joys of astronomy. And that is H2 is a homonuclear molecule. So that is, these are giant molecular clouds. The most abundant molecule is molecular hydrogen. And that's what I want to normalize to. This is a homonuclear molecule. There's no charge difference, so there's no permanent electric dipole because there's symmetry, right? In addition, due to spin statistics, that is, the hydrogen could have 2 spins up, or you could have 1 spin up and 1 spin down. And the 2 spins down is degenerate with 2 spins up, okay? They're actually, depending upon the spins, they're 2 independent molecules. When I first learned this, my brain exploded. All right. Hydrogen doesn't have a dipole, but it actually does have a quadrupole. And what quadrupole transitions is, they don't have delta J equals 1 transitions, they have delta J of 2. So the first transition is labeled is the 2 to 0 transition, often labeled as S0. I don't want to get into that. That has an upper state energy of 510 Kelvin. If I take my Boltzmann equation, remember that I showed you earlier, where the upper state over lower state, so the upper state is 2, lower state is 0. This is 510 Kelvin. I know what these are just numbers, okay? And I stick that in, that's what that is there. And I take a temperature of a typical molecular cloud, say 10K, e to the minus 51 is a really small number, all right? There's very little hydrogen in an excited state to emit and for us to detect it. So even though these are molecular clouds that are hydrogen molecular clouds, I can't see the hydrogen. And so that's where the density is, that's where the temperature is, right? The density of H2 is what I'm quoting for you for densities. The temperature of H2 is what I'm quoting to you as the gas temperature. But I can't observe H2. So what do? We observe other molecules, such as carbon monoxide, all right? And often we can use the dust as well, the dust, the emission from the dust itself. And that can be used as proxies to get the density of H2, the mass of H2, the temperature of H2, and even the velocity field of H2. So how do we do that? All right. So in a two-level system, remember I talked to you about spontaneous emission. This is spontaneous or stimulated emission. This is absorption. Okay, these are radiative processes over here. Well, things are also banging into each other. All right, that is, there's collisions that put something into an excited state or bring it out of an excited state. And so I can write down the equations of equilibrium. If I'm in equilibrium in a two-level system, what goes up must come down. I have my stimulated terms that link to the radiation field, right? Because they link to radiation. My collisional rates link to density. That's the spontaneous term. That's the stimulated term, link to density. So you may be figuring out what's going on here. If you're in a system where collisions are dominating, all right, I can actually determine the density of H2. Furthermore, these quantities here, these collisional rates, are temperature dependent. So I can also, if I have enough observations, determine temperature. And this is just breaking it down. So if I'm in equilibrium and I'm going to ignore radiative processes, so I'm going to zero this out. Okay. My collisional rates are related by this thing. There's my Boltzmann quantity. Again, these are just givens. I can break this down here that I have the collisional rates give me this term here. That's the kinetic temperature of the gas. This is what the molecule is seeing. We call that an excitation temperature. And I'll show you why the excitation temperature may not equal the kinetic temperature and how we can derive these various quantities. This is my spontaneous emission. That's the collision rate. There's my density. All right. So this is very simply, I can break this thing down. And if the collisions are dominating over emissions, all right, if this term here is bigger than this term here, then this goes to basically nothing. And I'm left with the kinetic temperature equals the excitation temperature. All right. And if I'm below that, and that's when you're in LTE, if I'm below that, you're not in LTE. So, all right, what does this mean? This picture shows it to you. This is the excitation temperature here. This is density. This is the CS, one of the molecules. This is the 2-to-1 transition. And you're looking at the excitation temperature. What is the excitation temperature for the 2-to-1? N/2, N/1 equals, I'm running out of room. That's a E to minus delta E over T. All right. I know I'm losing you, but bear with me here. As you get to higher and higher density, the excitation goes up, 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 until it saturates, and it saturates at the kinetic temperature of 10K. So what does this mean? This means this molecule and its emission depends upon, in some way, on the density of hydrogen and the temperature of the gas. So I can use, if I observe different rotational states, I can use that to determine the density. And similarly, I can actually use that to determine the temperature. And the neat thing is, not all molecules are the same. That is, the density where this transition here, you see where it basically saturates into the 10K, it's different for different molecules. This is for ammonia, it happens earlier, and for CO, it would be even earlier still. We define this as a critical density. That's the Einstein A coefficient, the spontaneous emission coefficient, divided by the collisional rate. And this is what the A coefficient is. All right. And you can see different molecules have different dipole moments. So their Einstein A coefficients are different. And what that means actually is that CO emission traces lower density gas than does all these other molecules. So if I look at, and I'll show you a little bit later, the CO emission is much more spread out than is HCN emission. And that's because of its dipole moment being different than that of other molecules. All right, I'm not going to get into this. All right, so I've talked to you about how we can get different quantities. All right, that is, I don't want to lose everyone with too much jargon. All right, I can observe multiple lines of a given molecule. So I can observe CO in the J equals 1 state, J equals 2 state, J equals 3 state. From that, I can actually determine things like the temperature of H2. From that, I can determine the mass of H2. All right. And I can also try to determine the density. I can observe different molecules that have different dipole moments, and things that are heavier trace denser gas. So HCN traces denser gas and CO traces lower density gas. I can use that as a powerful tool to try to extract and understand how the galaxy operates. And that's what I'm going to try to explain next. All right. So now we're going to do a survey of the various regions of space. And I'm going to start with what I'll call diffuse molecular clouds. All right, diffuse molecular clouds are a transition between the regions where stars are being born and my average density of 1 particle per centimeter galaxy material, galactic material. All right, what we do with diffuse clouds in astrochemistry is we use them to sort of say, well, what are the initial abundances before a star is born? In other words, what's in the gas, what's in the solids before a dense cloud goes on its way to making a star? What is the initial chemical state? Now, what matters here is diffuse clouds are, as we say, diffuse. So astronomers are very literate, like giant molecular clouds are huge, massive clouds of molecules. Diffuse molecular clouds means that starlight pervades them. That means radiation matters. And it's not necessarily the radiation of the nearest star. right? The nearest star could be an M star, and they're very puny in ultraviolet radiation because that's what matters. That's what destroys molecules. But it may be the generic interstellar radiation field. Okay. And what we do is we take a star, such as this one here, this is Zeta Ov, that is behind a molecular cloud. And the molecules in front of that cloud absorb starlight. And so you see the emission from the cloud sets a continuum, and where the molecules absorb, it's telling me how many of the molecules are there. Okay. And so I can use that to understand the initial chemical conditions. And the neat thing is in the ultraviolet, which is where a lot of these observations are done, you can also detect H2 in absorption. So this is what I'm talking about. This is density or column density in this direction. Okay, so I'm getting denser and denser heading this way. And this is abundance. Okay, so diffuse cloud, you have hydrogen, and then you form H2. All right, and you can see this is what we call a diffuse molecular cloud. This would be a diffuse atomic cloud. And then this is called translucent. Not going to worry about that. The carbon would be doing this. Most of the carbon in the galaxy is in ionized form. Why is that? Well, UV radiation keeps molecules from forming. And further, the carbon has its ionization potential below that of 13.6 eV, which is the hydrogen limit. All right. So that is, there's no photons going through the galaxy at energies greater than 13.6 eV in the ultraviolet. There may be X-rays, gamma rays, right? But in general, in the UV, H2 regions where near massive stars trap all the ionizing radiation inside of it. So if you have an ionization potential greater than 13.6 eV, such as oxygen, most of oxygen is in the neutral form. Carbon, in this instance, is in the ionized form. As you get to denser and denser, you get more absorption of starlight, you form neutral carbon, and then eventually you make your way into forming CO. And that's the structure, the chemical structure of a molecular region. So what we want to look at these things to set the initial chemical conditions, we have to understand something about standards, right? Hydrogen is our standard that we're going to go by, but the star, and in particular our sun, represents another standard. And so these are the solar abundances of various elements, and you can see very interesting structure, right? Very little beryllium. There's the iron peak, and that's telling you something about nuclear synthesis in the galaxy 14 or 4.6 billion years ago, okay? And I give you the references. So this is the sun's reference. There's probably even a more recent one. Now, this is the sun, right? This is what the abundances of all these various elements are 4.6 billion years ago. We can use B stars to tell us what the cosmic abundances are in the galaxy, the local galaxy today. So why do we do this? What we do is we observe, say, carbon and oxygen in the ultraviolet towards that Zeta Ov cloud. And what we find is, for example, for oxygen, not all of the oxygen that we expect to be there is there. All right, so what do I mean by that? So actually, it's probably better to think about it with iron. Most of the iron that we observe towards that Zeta Ov line of sight, this is normalized to the sun, is depleted. Now, why is that? What does that mean? So I'm looking at a gas phase emission line, in this case, or absorption line of an iron atom in this instance. where I could be observing a molecule, but this is an atom. And I normalize it, and I find that most of the iron is not present in the gas. Ergo, where is it? It should be there. Well, it's in the dust. That is, the silicates have formed, and most of the iron is in the dust. And so molecular clouds are made out of carbon. Half the carbon is in the gas. Most of the nitrogen is in the gas, and a good fraction of the oxygen is in the gas, whereas all the heavy elements are in the dust. So this is, it makes sense why we're seeing things like HCN, N2H plus, CO, and I'm not seeing things like FEH, right? Because the iron's not in the gas. Neat little thing, this is just an aside. If you look at meteorites, the most primitive meteorite, the CI chondrite, has the same abundance as elements in the sun, by and large. This is the abundance of elements in CI chondrites versus the solar photosphere. And just, it's fascinating. It's basically 1-to-1. And in fact, in some instances, when they can't observe the abundance of an element in the sun, they go look at it in a meteorite. Now, if you're a scientist, you're looking at this and you're saying, well, I don't know what the heck this guy's talking about. There's all these other things here. What's that? Well, those are noble gases. Noble gases don't react much. They don't go into rocks, but they're in the sun. Hey, that makes sense. What's that? That's lithium. Lithium is present in the chondrites, but it's underabundant in the sun. Well, stars burn lithium when they're young. What's this? Nitrogen and carbon are not in the rocks, but they're in the sun. Well, that's because a good fraction of the nitrogen and carbon didn't make it into the rocks in the asteroid belt. They must have been in the gas. So it's like little stories to tell. And the neat thing is, if we look at, this plot is showing whether molecules are in the gas or the dust. So if they're down here, they're dust. And up here, they're in the gas. And you plot it versus the condensation temperature, that is the temperature at which minerals form. You find that the things most missing from the gas are the things that are related to mineral formation. So that's another neat little factoid. All right, I talked about the fact that molecules get absorbed, molecules are destroyed by ultraviolet radiation. And the galaxy, when you collect regions into denser and denser areas, the dust absorbs that ultraviolet radiation. Why? Because the typical size of a dust grain is about the same wavelength as an ultraviolet photon. And the physics of excitation is such that a particle will absorb most efficiently a photon that has a wavelength about the same size as that molecule. So dust preferentially absorbs UV. And this is showing you a measure of that absorption. That is, this is high absorption, and this is low absorption, and this is UV, and this is headed to the visible infrared part of the spectrum. And you can see that in the galaxy, this is what's called an extinction curve. The dust absorbs more starlight preferentially in the UV than it does in the optical and in the infrared. And this is a really beautiful paper a while back that's showing you that different parts of the galaxy have different amounts of dust, what we call extinction, but you can think of that as absorption. So what does this mean? What is extinction? Extinction is the removal of starlight. That is, the starlight gets absorbed by a dust grain and heats the dust grain up a little bit, and the dust grain re-emits that photon, if you will, at a different frequency as heat. Basically, it gets emitted in the far infrared part of the spectrum. And as you imagine, if you have a star that's 200 parsecs away from the Earth versus a star that's a kiloparsec away from the Earth, right? The star that's further away from us has to traverse, its photons have to traverse through a greater and greater amount of interstellar material, and it will suffer from greater and greater extinction. All right. And this is just a facet of astrophysics that we have to understand what's between us and the source often as we do other things. And the dust, based upon models, is made of both silicates and also carbonaceous material. And this is one model, that the quantity on this axis is a very complicated quantity, but what that is, it's a sort of a size amount normalization, and this is versus size. And so the silicates, there's more silicates here at smaller sizes than there are at larger sizes, and carbon is doing something slightly different. Not going to get into that. This is another way. This is, I think, a more intuitive way for me to understand what do I mean by what the dust is doing to light. And again, why do I care about this? Because an object is a certain point of the galaxy. I need to understand its local environment if I want to study its chemistry. All right. And so that means I need to understand how much ultraviolet radiation there might be present in that vicinity. All right. And so this is a measure of extinction again, just the amount of starlight that's being left versus wavelength. And this is the ultraviolet high extinction. This is heading into the infrared low extinction. So stars, I'll show you this in a little bit. Young stars are buried in cocoons of dense material. That starlight is getting absorbed by dust grains. And so we don't see the actual starlight, but if we go to longer and longer wavelengths, we can start to peer through that material and actually start to see the star's emission. Okay, so let's get to some applications here. There were studies of hydrogen emission and the extinction of dust, the absorption of dust, if you will, done in the 1980s that are fundamental to our understanding today. And that is, we look at the galaxy at the amount of H or hydrogen that's present versus the amount of extinction. This is denser material, lower dense material. There's this correlation here. Okay, that is, as more dust gets concentrated, the more hydrogen molecules there are. All right, and I'm not going to get into the numbers here, but you can actually figure this out. And if I measure the extinction, which is in units of magnitudes, I can actually determine the amount of hydrogen that is present. That's actually a very powerful quantity. Look this up. Understand it. I'm not, in this amount of time, I cannot get into this stuff, but this is very important. Okay, so diffuse clouds, I can actually set the conditions. And what I've learned from diffuse clouds is most of the metals are gone. and my carbon, nitrogen, and some oxygen are around to make my molecules. This is the Orion B molecular cloud, just a molecular emission. This is the emission of dust, and I see these filaments here, okay? This is when I observe it in CO, 13CO, here's SO, CN. And, you know, when I told you every molecule is its own story, well, there you go, folks. Every molecule is its own story. And why is that? Why do these things look different than each other? Well, in some cases, it's having to do with the emission. CO is optically thick, and I told you it traces more the surfaces of the object. It also has a much more distributed emission than does, say, something like SO here. Why is that? That's because CO is tracing the low density material, and all these other lines here are tracing the denser condensations. All right. This is another perspective. I love this particular image. This is the Orion A filament. This is just, again, another molecular region. If I look at this in the dust, and I'll talk about dust in a little bit, the solids are absorbing starlight and emitting, right? So that's bearing information as well, okay? So this is the emission of the dust, and there's all these little, where it's denser here, this is where the stars are being born. And this is from Alvaro Carr, where he looked at this in N2H plus and saw this tremendous filamentary structure, cores here, and each of these things are where stars are being born. And you basically can trace stellar birth here. This is actually from my thesis, published by Ungerix et al. 1997. This is a tiny region of the Orion molecular cloud, but it's in a bunch of different molecules. So you can see here's CO, widely distributed. Its emission is optically thick. As I go to a lesser abundant isotopal log, I start to see more structure. Why is that? Because the CO, I'm only seeing the surface. 13CO, I start to peer deeper. C18O, deeper still. This one is telling me the mass of this object, the dense regions. I have other molecules tracing the densest part of this filament. And then some things are showing completely different. This is a molecule right here that's only emitting mostly in the northern part. Why is that? Well, that's something to do with chemistry. Another molecule only emitting in the northern part. Something to do with chemistry, something perhaps to do with also stellar birth. Here are molecules that are emitting as gigantic bullseyes in the center here. What is that? Well, actually, in the center of this object, this is where a cluster of massive stars are being born. This is chemistry. And what we can do is this is HNC, J equals 1 to 0. From that emission there, I can determine the column density in the J equals 1 state. If I know the temperature, and there are ways that I can determine the temperature, I can determine the fractional population in the J equals 1 state. And from that, I can get the total column density of HCN. And, I guess this is HNC. All right. And then if I have some way to get the H2 column, and actually I get it from CO, I have abundance. And that was basically my thesis, determining abundances and trying to explain all this stuff. Now, I told you that the dust also bears information. The dust can do a bunch of different things. The dust can absorb starlight. That's extinction. So here is a a 2 micron image of an object. And what I see here is this is the star field. And here you see the stars appear to be red. And that's because the dust is absorbing starlight from stars in the back of it. Okay. That absorption bears information on the amount of dust that is present. And you observe, if I were to plot the amount of dust that is present, that's basically what this quantity is. There's more dust here than there is there. All right. And so I can actually trace the density structure of dust in this object. And actually the dust is related to the gas. Observations in the interstellar medium have shown that the amount of dust correlates with the amount of gas. That works until you get to the disk where planets are being born. So that's really powerful. The simplest way to describe that is in interstellar space, the mass of gas, of H2 gas, is about 100 times that of the mass of dust. Okay, so from that information, I can take and determine from dust what is going on with hydrogen. This is the emission at millimeter wavelengths now of the dust. So the starlight is being absorbed, it's being re-emitted. In this case, we're seeing it at millimeter emission. All right, and if I look at that, this is a different object, but it's peaked at the center and decays down. All right, this is the emission. This is more dust here, less dust here. Well, actually, that is telling you that this object here is centrally concentrated. And the gas density is higher at the center point than it is at the edge. And there's another way to do it on the other side there. Okay, so then the neat thing is, what we're able to do is we're able to basically use the dust. This is the amount of dust. Dust in this figure, and this is the amount of C18O, or C7TO in this case. All right, and this work here, this is a classic paper that's lost to the sands of time. But what they showed is that the amount of C18O correlates with the amount of dust. All right, and if they then correlated the amount of dust, in this case to hydrogen. And when was that? That was the paper in the 1980s that I alluded to, where you had the H2 column density versus dust. And from that, they were able to derive a standard abundance of CO. So that is, I can observe CO, and so in this case, C18O or C17O, and I can determine the amount of H2 that is present. So to give you an idea, that's what we did here. I have my total column density of HNC. I can get the same quantity for C18O. And with this number, I can know how much H2 is there and determine an abundance. It's pretty cool, right? And this is just to show you, I did a correlation, trying to look at what do we know about the CO abundance in different objects. And these are all just different techniques, okay? And the neat thing is this is a linear scale. There are not many things in astronomy that we know to within factors of 2. And the CO abundance, the amount of CO in the general interstellar space, is known to within a factor of 2. So we can actually use all this information. We can look at these dense cores before stars are born. I can determine their densities, their temperature, their masses, and relate that. How much mass is there in gas versus mass of that in stars? That's what's called the star formation efficiency. Again, learning about stellar physics. And this is I think, I love this figure. It took me a while to make it. This is the dust emission in one object, all right, where it's centrally concentrated here. And there's a little tail going off here. And this is what we look at it if we see C18O. This is a different molecule. This is another molecule. And what's going on here? Well, here in the center of this object, I have a depression in the C18O abundance, but my N2H plus is going up. What the heck is that? Well, it turns out, if you think about it, this gas is really cold, 10 degrees above absolute zero. As I get to denser and denser regions, the molecules are colliding with grains. And basically, CO molecules in the center of this object are hitting a grain and making CO ice. That's pretty cool, right? So this depression is happening because CO is going into the solids. But then another thing happens, and that's what's going on with N2H plus. N2H plus CO makes HCO plus something else, okay? So N2H plus is rising because the abundance of CO, it's the main destroyer of N2H plus, is going down. All right. So when the CO starts to freeze out on the grains, N2H plus peaks up. All right. So you may have noticed that there have been numerous times I've showed you emission maps of N2H plus. I started at the beginning of that. I showed you the filament of Taurus, N2H plus, Alvaro Carr's map of Taurus showing these filaments of N2H plus. N2H plus was isolated as the tracer of the beginnings of star birth. Why? Because most other molecules were freezing onto grains. They weren't present in the gas. I'm observing gaseous emission. So they're not tracing the densest regions. The densest regions are where star birth is going to occur. N2H plus, because of the chemistry, all right, emits in the regions where stars are going to be born. So that's kind of cool. Now, I also told you that we can trace motions. That is, if I look at my molecular emission, the molecular emission doesn't come out as just one frequency. There's a spread depending upon the velocity of the molecules because of the Doppler effect. All right, so there is a line width. And so this is the C18O emission in that one object. And this is the line width. The line width has some spread and dispersion. But the neat thing is we can also look at the centroid of the line. And we observe if I'm over here, it has a different velocity than it does if I'm over here. This object is rotating. All right, so we can also study the rotational structure from objects. And this is really, really neat because you can look at things like the angular momentum versus star formation. So this is angular momentum versus size. And there is basically a loss of angular momentum all the way to go to starburst. And this is a wonderful paper, Bodenheimer annual review. It's an older paper, but really, really neat paper talking about the angular momentum problem in star formation. Basically, you have to lose angular momentum. And how did we know this? It's because we observed the rotational emissions of clouds and cores and studied it all the way down to stellar rotation. I'm going to skip over. I was actually able to prove that the CO was freezing out. And the other way you can prove that things are freezing out is you can actually observe ices. Molecules, when they're in the ice, they can't rotate, but they can vibrate. And if you have a background source that is shining through those ices, it can excite some vibrations. And when the exciting of that vibration is an absorption of that photon from the background source. All right. So the amount of ice that you have on a given line of sight leads to greater absorption. And this is a beautiful, wonderful paper from Melissa McClure, one of the first observations from James Webb of ices. And we can see water ice. Okay, and from observations of water ice in the chemistry, we know that water forms mostly as ice, whereas carbon dioxide forms mostly in the gas. And that's from observations. And here are things like methanol, ammonia, methane, CO ices, CO2 ices, and all kinds of other fancy structure. And you can read the paper, and there's going to be a lot more where this comes from. Okay, now we have a dense condensation. It's collapsing, gets denser and denser and denser. Bang, a star is born with a disk of material and a surrounding envelope and outflows and all kinds of other things. What happens when a star is born, these ices that are building up in the colder stage sublimate back into the gas. And it turns out that most of the organic chemistry in space happens on solids. All right. And how do we know this? That is because we see things like methanol, for the most part, its strongest emission are in regions that are very hot, greater than about 100 Kelvin, and very close to a young protostar. All right, so the full chemistry of space gets revealed around protostars. So these are what we call hot cores or hot corinos, where you have a warm envelope of gas surrounding a young star where ices are sublimating. And we tend to see this for the most part around massive stars, and that's historical, that they were easy to detect. But now with ALMA, we can look at hot cores, and they're so-called hot corinos towards solar-type stars or even lower mass. And this is what a protostar looks like if you were to look at its spectral emissions. So this is emission versus wavelength. The starlight should be emitting here, and we see no emission. Why? Because there's a dense cocoon of gas. All right. And instead, what happens is you have the starlight gets absorbed and the dust, and it's re-emitted in the far infrared. And so Herschel did this beautiful stuff where you looked at regions in far infrared emission, and you can see all these little dots here. These are tiny little protostars, baby stars. They're stars that are about 1 million years old. All right, and if we look towards these regions, particularly this is towards the massive regions, this is what a spectrum would look like. And this is a bunch of different regions, all right? I'm going to zoom it out. This is what you're looking at are different rotational states from CO that were observed. This is with the Herschel Space Telescope. And there's a bunch of water lines. You see these strong lines. All right, and these are all just different regions, okay? And these are molecules basically saying, hey, I'm here. All right, and I'm going to zoom in. What you see there is this. This is methanol. And it's, okay, that's methanol saying I'm there. And from this structure, I can determine the amount of methanol that's present. I can determine the temperature of methanol that's present. And what you can observe is in different regions, there appears to be less emission. There's very little here, little weak here, really strong here. That may be because the object is so far away, right, that I can't detect the methanol. That's actually not the case here. It's because this object doesn't have any methanol, whereas this object has a lot because the ices are sublimating. And this just shows you the different rotational states. This is what a spectrum looks like of methanol. These are all lines of methanol and a bunch of other things. And from this, as I told you, we can determine the density and the temperature. And just to show you from that just one of those spectra, we detected all these different molecules. And we were able to determine abundances of these molecules. So just to give an example, these are the emissions of methyl formate. And from our LTE model, we were able to determine the amount of methyl formate that was present from all these bajillion transitions. And we fitted that entire spectrum and basically did chemistry. And that's what we have. This is abundance relative to H2 for a bunch of different regions. And you take a molecule here, let's say, where's methanol? It's being hidden from me. It's methanol only shows up in one area. So that's telling me something about that object, and it's up for me to try to figure out what that is. And to analyze these spectra, there's a bunch of suites that you can use, and the references are provided here. The neat thing is, from the emission, you can also determine things like the line of sight structure in abundance. And this was some beautiful work done by some individuals working with Avina van de Schock. And this is a spectrum. And from the spectrum, we see emission. And then this is an absorption feature. And this is telling you that there's some cold stuff that's absorbing in front of some warmer stuff. And so Avina was able to show, or Avina's students were able to show, that here's the cold stuff and here's the warmer stuff. And they were able to work out the water abundance along the line of sight. I'll skip over the complex molecules so that we can get to disks. So disks, there's a whole bunch of tools that you can use to analyze disks. There's things that you can do for the radiation of dust. This is for the radiation of gas. These two are gas. These are dust. And these are models to do the chemistry. This model is public. These two models you have to ask for permission to use. So a disk has a bunch of things going on. Now the envelope is gone. And if I look at my spectral emissions, I can actually see the star. All right, but some of the starlight is being reprocessed and emitted at longer wavelengths, and that's the disk. And what we're looking at here is mostly the emission from solids. Okay, and you could take these emission that you're seeing here, and beautiful paper here by Calvin and D'Alessio showing you that this is a disk of material. This is radius and the height. The disk is warmer on the surface, all right, and colder as I head to the midplane, and the midplane has higher densities than the surface does. And I'll skip over the dust. I already showed you how the dust emission can track H2, and this is observations from Andrews showing you the amount of dust versus radius for a bunch of different disks. And this is telling you about the mass that's available for planet formation in each and every one of those disks. And that is because the dust emission that we're seeing here, okay, bears information on the amount of dust that is present. And if I make assumptions about how that dust emits, all right, and that's what's encoded in the equations here that you can look at, I can then extract the amount of material, and that's what Sean is plotting here. All right, the interesting thing about dust is the average dust size in interstellar space is about 1/10 of a micron. But what happens in a disk is that the molecules, it's dense enough for the dust to start hitting each other and growing. And as it grows, it sinks a little bit. It basically gravity. And eventually you get a dust-rich midplane. All right. And the dust can move around different ways, but the dust-rich midplane is where planets are born. And this is what we see. This is molecules, or I'm sorry, not molecules. This is the emission from dust in the closest, nearest disk, the TW Hydra disk. And you can see here, there's more emission closer to the star, colder further away. Why is that? That's because the dust is hotter, close to the star. That totally makes sense. But then there's structure here, right? There's a big gap here. There's something going on here, something going on there. Those little bumps and wiggles are telling us something about planet formation. And that's still an argument today as what that something is. One possibility is that it's planets. That's what's being shown here, that if you have a planet in the system, through its secular interactions, it can carve a gap in the gas and the dust. And so these are observations of a whole suite of other objects. And you can see here's the star in this object. There's a big gap here, another gap here. That may be due to the presence of hidden planets. We're still trying to find that out to this day. This object actually shows a spiral. And that object, we think, is actually gravitationally unstable. And the other thing I like about this image is this is from the Atacama Ray. Again, this is the millimeter emission. These are millimeter-sized particles that are emitting reprocessed starlight. But you can see the different orientations of these objects on the plane of the sky. It's just fascinating. And I'll let it run through. There's a bunch of different objects with my little squiggles on there that now have less meaning. And so the interpretation from this observation here is that this is maybe I have to go back and redo it. What that plot is the number of exoplanets that had been detected circa 10 years ago. Okay, it's a plot. If you're in astronomy, you'll see a lot. So planet mass here, all right, versus semi-major axis, and so that's semi-major axis, planet mass. These are all different planets. These are the planets that are inferred to be present based upon those ALMA images. And what's going on again is when you look at that structure in the dust, we interpret the regions where it's dark as being less dust. So a planet that's carving a gap will have less dust and also less gas. This is a similar set of observations, but only now looking at it from the emission from the molecules. So these are 5 different disks seen in, let's see, we have 13CO and C18O. And so you can see here, this disk, there's a gap here in the C18O, right? That again is interpreted as being due to hidden planets. And I'll skip over that because I want to get to abundances. So the last thing I want to talk about is in protoplanetary disks, we have a big problem. In the interstellar medium, we use 2 things as our proxy of H2. One is the dust, because we can use the emission or the absorption of the dust to tell us something about the gas. And the other is CO, because I have a calibrated abundance of CO, which I can then use to tell me something about carbon monoxide. And so I can observe, say, the C18O images that I just showed you and get the column density of C18O, but I can't get the column density of H2 because what we found is that in disks, the CO abundance starts to change. And in disks, the grains are growing to planets. And we can only detect dust grains up to about 1 millimeter size. If you have meter-sized bodies or planetesimals, which are 1,000-kilometer size or 100-kilometer size bodies in those disks, we wouldn't even know they're present. All right, so there's a problem with getting the H2 gas mass in disks. And one way you can get around it is by observing hydrogen deuteride. All right, and that's what I was able to do in a detection in 2013. There's the HD. And from HD, you can actually determine the amount of HD, you can determine the mass of hydrogen. Not easily done, but this is a plot showing the abundance of CO that we estimate versus age. And you can see that there's some evolution. And we do not entirely understand what that evolution is and what is causing that. And I think I'm coming down to the end. This is just showing you 5 disks in a whole bunch of different molecular emission lines. And you'll see that there's all I love this the C2H that's going away now. It has some beautiful images, and HCN. Look at HCN, which is right in the middle of the screen now. In one of the discs, you can actually see that it's cupped. And this is a student of mine, Felipe Alarcón. I had him make this plot, and these are the intensity distributions of the molecules versus radius. And you can see it's almost like each molecule is doing something different. It's like, what the heck is that? How can you explain that? And the answer actually is we were able to explain this by using very detailed molecule models subsequently. And so in observing molecular emission, we can do chemistry, and other people talk to you about the models that we can apply, and we can try to understand what that is telling us about star birth, what that is telling us about why we are here, such as observing water in all the various different phases, and so on and so forth. And these abundances that we're observing are used to compare to atmospheres, get the gas physics, when giant planets are born, the chemistry of planet formation, Earth's ocean, cometary composition, and I've spent much of my career to trying to determine how the Earth came to be. All right, and right now, of course, it's the time of James Webb. I showed you some of the ices already. This is another example where we see observations of various ices and some bending modes of CO2. And here's gas phase emission lines of various molecules. So this is CO2 gas phase emissions, hydrogen cyanide gas phase emissions. This is a beautiful observation showing C2H2, benzene. Why does this disk look different than this disk? This is the same wavelength, 15 microns, right? They actually look completely different. That's telling us something of planet formation. And my slides have explanations on what's going on here for the structure of these emission lines. But I'm gonna leave it right there and take your questions. I know that I went through this quickly and I did my best. But what I wanted to give you was the tools that you can use to study star birth. And so that these slides can be basically a template for you as you try to understand and navigate astronomy. All right, I'll stop there and take questions.
Yeah, thank you, Edwin, for very interesting and informative lecture. So we start with a question session now. So I can already see a number of questions in chat. So let's go on. The first question, given the many more excitation modes available to molecules as opposed to atoms, are there spectral features that are similar between molecules? And if so, are there techniques other than go get some laboratory spectrum, which can help untangle the one from the other?
Yeah, no, that's a good point. And I didn't get into that. I mean, I talked about the simple theory of linear molecules. I'm going to stop sharing my screen if I can here. Maybe. All right, well, not going to be able to. So there we go. So for linear molecules, you can sort of use that simple theory. We don't use that anymore. Everything that we do is using spectra that were determined from laboratory work. So when I showed you those complex spectra, and we were able to know where a given transition is where, and methylformate, I was able to know that all these bajillion transitions were from methylformate. That's from laboratory work. And there's detailed laboratory information that is provided on the web, and then we extract that and apply that to our observations. We would not exist without the very detailed work by laboratory astrophysicists. This field is insanely interdisciplinary.
Okay, thank you. And just a bit more specific, how about quantum chemistry? Would not it work with very high level quantum chemical calculation?
Yes, no, that's right. There's also theoretical aspects to the molecular excitation, theoretical aspects. So we need to have collision rates to get densities. Those are by and large determined by theory. And we didn't even, I don't talk about reaction rates and how an ice goes onto a grain, how an ice comes off a grain, how reactions occur on a grain. There's all kinds of other aspects where we link to chemical physics, physical chemistry, you name it.
Okay, thank you. So the next question. In the excitation graph, what was causing the knee in around 3 microns? I think it was related to one of the slides during your presentation.
Oh, there's a bajillion slides, yeah.
Yes, that would
yeah.
Be
so the,
okay.
At 3 microns, that's water ice. Okay, so water ice has one of its fundamental modes at 3 microns. There's another one at 6, and silicates are at 9 microns. So what you do is you take some of those templates that are out there, the McClure paper, and follow the reference trail to track back as what is emitting or absorbing at a given location.
Okay, thank you. So the next question, could you please explain why HCN and HNC maps look so different?
Damn good question. There's been a bunch of papers about that. Those are what are called isomers. They're basically the same molecule, but they have slightly different structure. And that is believed to relate to temperature. Okay, HNC is favored at lower temperature.
Okay, thank you. The next question. Can you determine the rate of the reaction between H2N plus and CO to form HCO plus in those regions? And if so, how accurate they are?
Sure. That's just one reaction rate that I talked about. Our models have hundreds to thousands of them. Many of them are determined, some of them, some percentage are from laboratory work, which is crucial. That particular reaction is what's called an ion neutral reaction. And you can determine that reaction rate by something called the Langevin rate coefficient. And it's a very simple theory, sort of like a billiard ball theory of collisions between atoms with different dipoles, or molecules with different dipoles. And you can determine that reaction rate and with decent precision. Of order probably a few 10 to the minus 9 centimeter cube per second is the number. I'm pretty certain that's the typical rate that you would get for that calculation. Our rate networks, our rate coefficients have been curated by individuals who have a greater connection to chemistry. And those of us who are more theorists or observers, such as myself, I use the information that others have curated for me to make sure that I'm applying the most up-to-date reaction coefficients that I can.
Okay, thank you. The next question. Can you give a general overview of situations where collisional excitation-deexcitations are important with respect to spontaneous or simulated emission. For example, in what kind of situation we can say that collisional excitation, de-excitation must be taken into consideration?
Welcome to astronomy, my friend. Is there a star there? Is there a source there? That's one statement. Okay. If there's not a star there, or the star is far away, then you're more likely to be collisionally dominated than you will to be radiation dominated. If you're somewhere parked next to the star, you always have to have the question mark in your brain. Am I observing collisional excitation, or am I observing radiative excitation? And many people have been wrong on both sides of that question. So you have to think it through.
Thank you. The next question. When calculating the optical depths, we use the intensity ratio of molecules isotopes. Shall we use the ratio of peak intensity or the integrated intensities?
Thank you for someone who's paying attention. That's more information than I gave, so good for you. In theory, they should be the same. If it's the same molecule, they should be emitting from the same region. And if the line widths are substantively different, okay, then they may not be tracing the same region, and the quantity that you will derive will not be as accurate, right? In general, I would use the integrated emission.
Okay, thank you. So the next question, when calculating the optical depths, we use in... Okay, no, that was the same. So the next question, any idea of how the more complex molecules formed, such as C2H5OH or NH2CHO, just comes? Yeah.
Sure. Yeah. So basically, what we know is that it's very hard for the gas phase to create many of those molecules. All right. So they have to be happening and forming on grains. All right. And so the initial models for grain formation said that the hydrogen atoms could zoom around on the surfaces, and the oxygens and the nitrogens are heavier, and they would stay put. So these are what are called catalytic chemistry, right? And you'll have to listen to some of the other lectures to get into the details on that. Obviously I'm presenting the observational extraction side. And so there are detailed models of that. There are some instances, however, where some complex molecules can form in the gas. But by and large, things that you alluded to, they are thought to form on the grains, not always by H atom addition. There's more complexity, and you can look at the work by Whittakus, Weaver, and Garrett, particularly Garrett.
Okay, thank you. So I have also a short question, because you speak mainly about the detection of the molecules in the gas phase, but you also mentioned the detection in solids, in ices. So how would you compare the sensitivity of the detection of those molecules in the gas phase in the ices? So
that's a clever question. With Spitzer, we could get down to ice abundances of about 1% of water. And if the water abundance was, say, 10 to the minus 4, we could get to abundances of maybe 10 to the minus 6 relative to H2. And I guess with Webb, you must be able to do at least an order of magnitude better than that. With the gas phase, we can observe abundances probably down to 10 to the minus 11 or 10 to the minus 12. So the gas phase is much more sensitive.
Many orders of magnitude, actually.
Yeah,
yes.
Exactly.
Okay, thank you. So the next question. Do you think with the advent of advanced experimental spectroscopical technique, theoretical quantum chemical spectroscopy studies will become obsolete. So basically, the question whether the quantum chemistry computation of spectrum could replace basically laboratory measurement.
I don't think so. You know, the some of this stuff is really hard to do theoretically, and much of what we do is based upon assumptions. I refer to my models as a gigantic, wonderful, beautiful, gorgeous house of cards. Okay, and so I have to be humble in application. So the theoretical quantum chemists are super smart and do some wonderful stuff, but the landscape is so vast that I think it would be hard for everything to be overtaken.
Okay, thank you. So we have another question. Is the planet formed the same time or after the star is formed? Say, is the Earth formed before the sun or at about the same time?
Sure. I was leaving to others to talk about planet formation, but I could have given you a whole other talk on planet formation with a lot less equations. First step is the star forms first with the disk. The solids grow first. That takes of order 1,000,000 years. And then planetesimals form, and then magic happens and you make planetary cores. And then you get to many Earth mass cores and make your giant planets. That happens of order slightly 1,000,000 years, 2,000,000 years. So you make your giant planets maybe 2 to 3,000,000 years. The Earth doesn't cease its formation based upon what we know until of order 30 million years later when it solidifies. So that meant the Earth was getting its butt kicked by other big solids that left it in the molten stage. So the Earth solidification, so terrestrial planet formation takes longer than giant planet formation, and the star forms first.
Okay, thank you. So the next question is, okay, I'm currently constructing a rotational diagram with the K letters of methyl cyanide to determine column density and temperature. Can you expand your knowledge about methanol rotational diagram? Can be used E and A isomer transitions of methanol in the same diagram?
I think you can. So what's going on here is that the lowest energy states. All right, so E and A are two different spin flavors of methanol, just like H2 has these different spins. Okay, hydrogen is the lightest, and the lowest energy states of those two different spin states are biggest for hydrogen. When you get to methanol, the difference in energy between the A and E states is only like a few Kelvin. Maybe it's like 5 Kelvin. I don't remember what the number is. But it basically would have to say for you to have a substantive difference between the A and E, you would have to have tiny little chemical effects that would occur only very defined conditions. It would be very hard to get A over E major disparities. And in fact, we looked at this for methanol in a protostar, and there's no difference. So I could tell you both theoretically, that was my expectation, and we just did it, and you go for it and don't worry about it.
Okay, thank you. So the next question, was HO2 cation detected till now? Similarly, neutral HCO detection?
HO2?
HO2 plus. Yes.
H2O plus. Yeah. Okay, that's my guess, as opposed to O2H plus. So H2O plus was detected with Herschel and exists only in the diffuse medium where there's lots of ionization. And it's a fantastic probe of the ionization state of gas. And in fact, has been detected at high Z. HCO is a short-lived molecule. and has been detected in PDRs, photo dissociation regions, and it must be being created as efficiently as it's being destroyed. And you can look it up.
Okay, thank you. So the next question, is there a way to determine whether the presence of CH3OH and silica oxide in regions with hot cores is attributed to turbulence or outflow?
Right. You see a line widths that are broadened, all right, and that broadening could be due to some sort of massive turbulence, or it could be due to an outflow. In general, tens of kilometers a second, that's an outflow. Turbulence, the turbulence cascade, when you get to that dense gas, maybe if you're close to the star, there may be some sort of turbulent motions, but what is probably giving rise to those turbulent motions are systemic motions, infall and outflow. And so when I think about turbulence, I like to look at the quiescent gas to try to understand that. Okay.
Okay, thank you. So the next question, how well do we understand dust extinction in high redshift galaxies? Is it comparable to that in local galaxies?
No, it is not. There's less dust. But what they're doing, what everybody's doing, is they're taking some emission that they're absorbing and they're making some assumption about how much dust is there, and then inferring, say, the star formation rate. So when we say the star formation rate versus redshift peaks at z=2, right? There are assumptions built into that calculation for their observations to extract out the dust and get rid of it. And so the way we have to do it is what they're doing now with Webb, is trying to directly see the amount of dust and work it back more explicitly, because Webb is a little bit more sensitive to what's going on with the dust. So the answer is no. It's a fascinating field. All right, I'll be with you in a second. Someone's at my door. Just give me a minute. Okay.
Okay, so thank you. Next question, I think, is clarification of the previous one. Okay, and the question actually whether the experimental spectroscopical studies will overtake theoretical studies, given the evolution of the later studies has been slower than the former, if I'm not wrong.
It's woe man power limited. Okay, so men and women have to go into the field and want to do it, get the money, and that's what's going to limit things. Okay.
Good. I think I don't see any further question here in the chat, and also our time is running out.
Yeah, I have to go to a next meeting, so.
Yeah, so let's thank our lecturer once again for a very nice and beautiful lecture.
All right.
And with this, I finish our today's lecture and see you all on 19th.
Okay.
Okay.
Thanks, everybody. Take care.
Thank you, and have a nice day.
Okay.
For everybody. Goodbye.